Coding 101 The Kids Way is an educational program which teaches kids ages 7 to 12 years all about coding and how coding impacts their world. The aim of the program is to inspire kids to learn how to code through practical experiences and insights to career opportunities. This outline was developed by Smart Kids Educational Club on behalf of Tambourine Learning for the Public Broadcasting Corporation of Jamaica.
Are you ready? Let's go! Wow! All right! Hi, mini coders! Welcome to another episode of Coding 101 The Kids Way. I'm Cece the Robot. I'm super excited about today's show because I get to share how to use code to control electronic circuits. But if you're new here, I'm your friendly robot who simplifies coding so we can all understand. We've discussed so much so far over the past couple of episodes, from coding, game development, and robotics. We even took it back to the basics and talked about what are the parts of a computer. Yeah, we discussed a lot so far. You can check out these episodes on our YouTube channel at PBCJamaica. Let's get started with this week's show! Welcome, mini coders, to Coding 101 The Kids Way. I'm Cece the Robot, and it's really great to have you guys here. Are you ready to learn something cool about controlling electronic circuits? Let's get right into learning about breadboards, inventors, and microcomputers. Are you familiar with the word breadboard? No? Well, it's not built out of bread for sure. The term breadboard comes from the early days of electronics, when people would literally drive nails or screws into wooden boards on which they cut bread in order to connect their circuits. A breadboard is a rectangular plastic board with a bunch of tiny holes in it. These holes let you easily insert electronic components to prototype. What does a prototype do, you might ask? Well, it's when you build and test the early version of an electronic circuit, like this one, with a battery, switch, resistor, and an LED, light-emitting diode. The connections used on a breadboard are not permanent, so it's easy to remove a component if you make a mistake. Or you can just start over and do a new project. That makes breadboards great for beginners like you who are new to electronics. You can use breadboards to make all sorts of electronic projects that are so fun, from different types of robots, an electronic jump set, to an electronic rain detector to help conserve water in a garden, just to name a few. Nowadays, breadboards are made from plastic and come in all shapes, sizes, even different colors. The most common sizes you will probably see are full-size, half-size, and mini breadboards, but there are larger and smaller sizes that are available. Most breadboards also come with tabs and notches on the sides that allow you to snap multiple boards together. However, a single half-sized breadboard is sufficient for many beginner projects. One of the coolest things a breadboard can do is to create an electronic circuit. Pretty cool, right? Let's learn a bit more from our friends at Quick Start Workbook how to actually build one. Grab your tools and let's go!
In this video presentation, we will design and build a simple circuit to illuminate an LED. So what parts do we need for this project? Well, to start off with, we need a breadboard on which we will build the circuit. We also need a 9-volt battery to power the circuit, and a means of connecting the battery to the breadboard. We can either do this using a battery clip or a battery box, whichever you prefer. We also need one 5mm LED. Popular colours are red, green, orange, yellow. You can choose whichever colour you want. There are plenty of other colours available as well as the ones I've shown here. And finally, we need a resistor which will be used to protect the LED. But what size should it be? To calculate the size of the resistor required to adequately protect the LED, we can use Ohm's law. So in order to calculate the resistance, we need to know what the voltage is and what the current is. So as stated here, the voltage is the battery voltage, which is 9 volts, minus the voltage drop across the LED. So the forward voltage drop is the voltage that is lost in the LED when it is operated at a certain current. If we assume a voltage drop of about 2 volts, which is fairly typical for an LED, then this gives us a voltage value of 7 volts, which is what we'll use in Ohm's law. And we also need to know what the current is. Most LEDs require somewhere between 16 milliamps and 20 milliamps in order to shine brightly, but without causing any damage to the LED. So 20 milliamps is what we will use in Ohm's law. If we now put the voltage and the current into the equation, we can calculate the resistance. To be on the safe side, we'll go for a slightly bigger resistor, say 470 ohms. The resistance value of a resistor can be worked out by looking at the bands on the resistor. For a 470 ohm resistor, the bands are yellow, which represents 4, violet, which represents 7. You can then put these two numbers together, which gives you 47, and then multiply them by 10, which is indicated by the brown band. The gold band at the end means that the actual resistance value will be somewhere in between plus or minus 5%. Now that we know which size resistor we're going to use, we can design and build the circuit. And firstly, here we have the circuit shown using nice little real-life images to make it easy to see where the components go and how they fit together. It doesn't matter which way around the resistor goes in the circuit, it is a non-polarized component. But the LED, on the other hand, has to be inserted with the long terminal, the anode, on the positive side of the circuit. Circuits are quite often shown using schematic symbols to represent the components, as shown here. And this is what the circuit looks like on a breadboard. Again, we need to make sure that the LED is inserted the correct way round. Here I've labelled the cathode, which is the short terminal. And here are a few photographs that show the actual circuit being built. So we start off with an empty breadboard, and then the first thing we can do is to add the resistor. Then we can add the LED. Here again I've labelled the anode this time, which is the long terminal, and also the cathode. And finally we can complete the circuit by adding the battery, so connecting up the positive terminal and the negative terminal. And it works. Fantastic.
Now that was fun! Remember to share what you've learned with others and get them involved in having a good time learning. We'll be right back with more information on the invention from our surprise guest. Welcome back, Minicoders! And if you're just joining us, I'm Cece the Robot. Before the break, we had a pretty interesting discussion about how to use code to control electronic circuits by using breadboards. But as you know, it doesn't end there. We have a guest computer engineer that I'll be interviewing. Hi, Shamir. What's up? My Minicoders and I have a few questions we want to ask you about computers. So, who's a computer engineer? What do you do?
Hi, CC. A computer engineer is someone that uses electrical engineering and computer science to develop new technologies, create new thing. And so some technologies that you're probably used to computer engineering being involved in is like your tablet that you use at school or your computer, right? Or they might be involved in some of the apps you use, like Roblox.
Which technical skills are required to program efficiently?
Right. To be a good programmer or to be efficient at programming, you will have to have some skill sets around development languages that might be useful. So, what's a development language? You can consider this as language that your computer program uses to know what instructions it should carry out. For example, if you're using your tablet and you click on an icon to open an application, that click, that functionality, that's a language that the computer is using or your tablet is using to know what action to take, right? And so to be a really good computer engineer, to be good at what you're doing, you need to be able to understand different languages that you can use to communicate with your computer or your device or your tablet, etc.
Which non-technical, that's soft skills, are required to program efficiently?
Right. So to be a good programmer, it's not just about knowing the languages that you use, right, CC? To be a good programmer, you have to have dedication. You have to be willing to learn the languages, learn the different programming techniques to be really good at your job. You have to have what you call initiative. So not just waiting to find out what you do, but it's about leading, right? Activating, knowing that a certain thing is required and you're taking the necessary steps to get it done. So, for example, let me break it down for you. Your teacher says, hey, I want you to develop a program that helps students study, right? And so you're thinking about, okay, how do I even go about this? And so taking initiative is important. So researching asking the teachers questions around what the application should do, etc. That's taking initiative. And so that's a big part of being an engineer, computer engineer, and programming is taking initiative and seeking out answers to be able to solve your problem, right? And so, those are two things that I think will stand out a lot, being dedicated and taking initiative.
Which programming language do you prefer when writing programming algorithms?
Specifically, CC, I love JavaScript. JavaScript is amazing, and JavaScript has the ability to create many different types of applications. So for me, I use JavaScript to create web applications, websites, and I use JavaScript to create mobile applications that you use on your devices on a daily basis. So for me, JavaScript is my language of choice.
I know I explained it earlier, but for those of us who didn't get it, what's a breadboard?
All right, so a breadboard is, you can consider this a circuit, right? Something that helps you do quick prototyping, right? So if you want to figure out quickly, how to connect how to have connectivity in your circuit to achieve a certain outcome, you can leverage a breadboard to test this theory, right? And say, for example, you have, something that involves some switches, some wiring, and what you want to be able to do is say, hey, if I switch this on, I want to see if the light turns on. And if I switch this off, the light should turn off. And so you want to have that connectivity on your breadboard. And so you can use that for quick prototyping to say, hey, if I do these sequence of steps, this is the desired outcome based on how you programmed or wired your circuit. A breadboard can help you achieve that quickly. And then once you've proven your concept, you can then go and buy and invest in much stronger technologies and hardware to be able to build this out completely. So for example, right? Say you had a toy car, and when you turn the toy car on, the toy car will start moving in a forward direction, around your house, right? That's a series of circuits and wiring that made that toy car move forward when you switched it on. But to test this technology, you'd use a breadboard to do the connectivity and put the wheels on, right? And then you'll be able to test that before sending it off to get built by manufacturers with more high-tech hardware and software. So the breadboard is the first step to doing that initial testing for your system.
Can you name the essential stages of the software development process?
So in software development, right, CC, software, and let me break it down for you. Software is like the technologies that you use on your tablet or computer to help you, use different programs to achieve things. You could use YouTube to watch videos and learn and study. You could use Microsoft Word to type documents, right? You could use Roblox to play games. Those are all software technologies. And so in software development, we have a process. We call it SDLC, the software development lifecycle. And so it goes through different phases. And in those, there's a couple key phases that are important to software development. There's the prototyping stage or the MVP stage, in which you try to figure out what's necessary or what's desired from the persons who are going to use your software. So, for example, I'm building Roblox. What are some of the things that the kids want to use when I'm building Roblox? So I think through that, and then we document it on paper. Then you go into building that prototype, and so you build the first phase of this. And once it's built, what happens is that you're now able to test the market with this particular product. And so you go through this testing phase. And then through testing, there's the outcomes of your test. So whether it worked or didn't work, what kids like or didn't like, right? And so you're testing the software. And then based on the results or the feedback from your users who are, who you're trying to target, you'll be able to make changes and improvements to the system. And so you do this in a circular process, right? You build, you test, you make changes, build, test, and make changes. And at the end, what you do is push your software to what you call production. And production is just simply saying, hey, I'm going to push this software to everybody in the world, right? So that they can use it. And when they do this, what then happens is that now you've gone through your iteration, your development process. And now you're pushing software out there that you want everybody to access, buy, use, whatever it is that your software is intended for. And so you go through this development process in a cycle until you get the desired outcome.
What would be your definition of debugging in software development?
All right, so debugging, right, CC? So remember I talked about the software development lifecycle, and I talked about the process that's involved in software development, right? So for us, debugging is a part of the testing phase, when you're testing and you're trying to fix things, right? And so when your users are doing that testing that I referred to in the software development process, what happens is that they're going to raise issues that happen. And the process in terms of investigating those issues and testing it is called debugging. And so in that debugging process, you'll be able to go through step by step the action that your user or the individual who was testing your application or using your application, you get to go through those step-by-step actions that they took in a slow and controlled manner so that you can pinpoint the exact area in which it failed or didn't work, or if there was an issue. And so debugging is that process in which you systematically or programmatically or step by step walk through the actions of that user so that you can find out exactly what went wrong and then fix it.
How are computer programs and computer software different?
All right, so computer programs, right, CC, are applications that are made available to users. It's packaged in a way in which, it's consumable by users. You can download it, you can access it, etc. Computer software, on the other hand, are the pieces that make up that program, that application that gets sent out to the different users. So the software part of it is the underlying technology that makes up the overall program. So you can think of it this way. When you're using Facebook or you're using Instagram, you're using YouTube, etc., these are all programs, these are all applications, but there's many components of computer software that makes up all of these things. And so when you're using Facebook, for example, there's a chat, there's a messenger, right, in which you can talk to individuals. That's a piece of computer software that focuses just on the chat component of the entire Facebook application, right? And so that chat software is just a piece of the overall program. And then you have what you call a news feed or an activity feed. That's another software component, computer software that makes up that overall computer application or program. So the program or application is like a package. Think of this as like a square. That's your program. And inside your square, you have many squares. And those are all your software components that make up your overall program.
How would you define software re-engineering?
The software re-engineering is where, say you have your the software components that you deliver. And we talked about chat, we talked about like a news feed or activity feed, right? And so sometimes you develop and push something out there, but by users using that software and technology, by them leveraging it and using it every single day, right? What you find is that improvements can be made, right? You can always make it better. And so the first version isn't always the final version of your software. And then so what happens is that sometimes you re-engineer it. You go back to the drawing board and you figure out what are the things that work and didn't work. And then you put things in place to improve it or make it better. And so you're re-engineering it, you're rebuilding it, right? And oftentimes you're doing so with information. You're using data-driven points to improve your solution. What is data, you might ask? These are all the statistics and points that you've gathered from all the users using your application, the way they use it, the way they click it, the way they navigate it, the way they move around your software, the speed in which your software reacts to the actions that they're taking. And you're using all those things to determine, okay, what best re-engineering steps should I take to make my application better? And so usually re-engineering helps make applications faster and better for the ones who are using it.
Cool stuff! I'm super excited to create music. Thanks, Shamir, for joining us. We'll continue on this groove when we return. Coders, welcome back. If you're just joining us, my name is Cece the Robot. Earlier, we discussed a whole lot about breadboards and how to use breadboards to create electric circuits. And we even talked to a computer engineer named Shamir. He was great and very educational. Let's watch this video on how to use a microbit to create fruity music. Let's go!
With this microbit, you can also make music. In this mission, we are going to program cool beats by using Fruit. And because standard there is no speaker in your microbit, we are going to hack that from earphones or an old speaker. By pushing on the one banana, the beat goes up, and by pushing on the other banana, the beat goes down. That's how you can produce music from the speaker. But how do speakers actually produce sound? Let's see. A speaker is a device with which electrical signals are converted into sound. There are different types of speakers, but the most common one is the so-called electrodynamic speaker. The core consists of a circular magnet with a groove in it, in which a spool is hung. The spool consists of wrapped copper wires. If you put current on this, a magnetic field is created. The permanent magnet also produces a magnetic field, and this way it can attract or repel the spool. This causes the spool and the speaker conus, the usually cone-shaped outer part of the speaker, to move back and forth. So by putting an alternate current on the spool, the conus can move back and forth many times per second. This causes alternate pressure on the air in the speaker conus. These differences in pressure cause waves that the human ear can translate into sound. These waves are expressed in hertz, just like your weight is expressed in pounds. And the higher the hertz, the higher the pitch. 1000 hertz produces a very high pitch. 100 hertz produces a very low pitch. So now you know how a speaker works. If you do not have a small speaker, then you can also use a headphone. That has two very small speakers. First, we are going to write the code. Navigate with your browser to makecode.microbit.org. Our code consists from 3 parts. Make a variable sound and drag from variables the setSoundTo block between the onStart block. Change the 0 into 260. This piece of code now sets the variable at 260 Hz, a tone in the middle between high and low pitch. Your turn. From input, take on pin P0 is pressed and change the P in 0 into pin 1. From variables, drag set sound to. And from music, drag play tone middle C for 1 beat into this block. From math, take 0 plus 0 and place it behind set item 2 on the place of the 0. Drag the variable sound on the first 0 and on the play tone middle C for 1 beat. Change 1 beat into 1/2 beat. Change the second 0 into 1/10. It now reads, if pin 1 is touched, then increase the variable sound with 110 Hz and play the variable sound for the duration of 1/2 beat. Your turn. Program the code and test it on the microbit on the screen. As you can hear, the beat gets higher all the time. I don't want the beat to become super high, so I'm going to add an if-then statement. I do it like this. From logic, I take if-then. Into that, I attach from logic the block 0 is smaller than 0. Change the first 0 into the variable sound, and the smaller than sign into larger than or equal with sign. From variables set item 2, I choose my variable sound. Change the 0 into 2093 Hz, and change the other 0 into 260. Now, if the pitch gets higher than 2093 Hz, my code will set it back to 260 Hz. Your turn. Duplicate via the right mouse button and click the entire block. Change pin 1 into pin 2. Change 2093 Hz into 65 Hz. Change the plus into a minus. And 110 into 35. Change the equal to or greater than sign into an equal to or smaller than sign. Can you think of what is going to happen now? That's right. If you now touch pin 2, the beat does not go up, but down. Your turn. The code is ready. Name it, save it. Download and drag it to your microbit that you have connected to your laptop or computer with your USB cable. I have added a link to the .hex file, just in case your code would not work for one reason or another. Disconnect your microbit and connect the battery pack. Connect the speaker to your microbit by using 2 crocodile clips. One to the 0 and the other one to the ground. If you have headphones, then connect the 0 to the bottom tip of the plug and the ground to the top part. Now connect one banana to the 1, and one banana to the 2. And the tangerine with a cable to the ground. Time to test. Hold the tangerine in your one hand and squeeze the bananas alternately. This is how you make fruity beats with your microbit. Oh, watch out. Are you using headphones? Test them first without putting them into or over your ears. The sound can be pretty loud, and you don't want to damage your hearing. Did it work? Awesome. Have fun making the beats and see you at the next mission.
Continue to dance to the rhythm of the beat. But I have to go, so thanks for joining us, mini coders. And remember, I'm Stacey the robot who helps kids to code. See you next time.